Hello, I am Dr. Rashid Ahmed from the Department of Physics of Kohat University of Science and Technology. In the subject of Mathematical Methods of Physics 2 with the course code PHY222, we are at the lecture number 16 and the topic is green function. In today's lecture, I will explain to you that how we can solve a second order linear differential equation with the help of green function. Previously, we talked about the second order linear differential equations and their solution, and we used different methods, for example Laplace method or other methods, but green function is a powerful method for the solution of second order linear differential equations. But today we will see that how physically it is a valid concept and mathematically it is useful to solve such equations. So let's begin with considering a differential equation of this sort. You see that this differential equation is a second order linear equation, because in the first term over here you see that we got a second derivative involved over here. This double prime notation means that we have second derivative, that is this is a derivative with respect to x. So y is a function of x, and y prime, by y prime we mean dy by dx. So when we have double prime, it means that we have a second derivative involved over here. So we have now here in this equation second order derivative in the first term. In the second term we have omega square, which is a constant. In physical problems it will appear that it is some kind of frequency you can associate with it. For example, if there is a string which is vibrating, then this will be the frequency of that vibrations. And a term multiplied with this is a y, which is again you see is a linear function because it has no second order power. It is no square or cube involved. It's just a power of 1. And on the right hand side of this equation, then we have some function of time. Here the role of the x is played by this t. So in this equation you see that we have a second order linear differential equation, or on the right hand side we have some unknown function. Okay, so we also consider the initial conditions that when t is equal to 0, we have y naught is equal to 0, and y naught prime, that is the first derivative of y naught, is also equal to 0. So this is our initial condition to solve this initial conditions to solve this second order linear differential equation. So what we want to do is to use Laplace transform of Dirac delta function to put this equation into a little simpler form. And this we can do by defining this function as a Laplace transform, as you can see over here, of a Dirac delta function. So you will see that this definition of a function we will use for the solution of this differential equation, and also the definition of a green function. Okay, so as I said that on the right hand side physically the physical meaning of this function is some kind of force or forcing function. So you can think of this f of t as a response of a system to the unit impulse. So let me explain this. So think of some system which is under the force. For example, you can think of a ball hitting a bat. Now when ball hits a bat, then there is a spontaneous force produced from the bat which is acting on the ball. We call it impulse. So let's say we have a unit impulse which is acting on just a single impulse which is acting on a ball, and if we want to check the response of the system, we have to integrate all such unit impulses to get the total response. And this response of the unit impulse, that is forcing function, can be then written as this equation, that is d square by dt square g of t prime. This g of this function g can be associated with the response of an to the unit impulse, and we will see that this function g is actually a green function. So it means that we can write the response of a unit impulse as g, and here you see from the previous equation we have just replaced y with the g and f of t with a Dirac delta function. So response of many such impulses, if you want to get the response of many, because this was the response to the unit impulse, remember this was the response to the unit impulse. If we have many such impulses, then we have to integrate this g or sort of calculate as a Laplace transform, and so this y is actually the amplitude or the response of many impulses produced. So this gives us the complete response after this integration of a green function over here. Okay, now if we substitute this into the equation, first equation, that is this one, that is y double prime plus omega square y. If on the right side we have f of t, just f of t we will bring in g later on, but first just tackle the left hand side, and this left hand side y double prime we know is actually the second derivative d square by dt square and this omega square, so we can take y common of this term. So you can think of it like this y square double derivative written here, and since this is acting on y, so this prime actually contains y, so it is over here, so it's acting on y as well, and omega square is multiplied with the y. So this can be written as, if we put the value of y as we have obtained on the previous slide, if we plug in this value of y over here, so you see in terms of the g we will get this equation, and then we can since this derivative and omega is independent of the integration involved, therefore we can just bring it into the integration over here, because you see that this integration is done on dt prime, it is not on dt t. So therefore this is t and this is omega, so both of them do not contain any t prime over here, so they will not be affected by the integration. Therefore we can just bring in this or inside the integration, and we will get this d square by dt square plus omega square into this thing. So this is the then complete integral. But we already know that this term is equal to delta function, Dirac delta function, and this. So you see that this green function solved the second order linear differential equation. So this is the way. So it's just acting like an operator on f and putting the equation in this form. Okay, so what is now green function actually? If we have the initial conditions that g is equal to 0 and the derivative of g with respect to time is equal to 0 at t is equal to 0, then green function, which is actually now a collective response, so to say, you can say that then in this interval it is equal to 0, and this interval you can like an impulse, you can think of it like an impulse of this sine form. So having these initial conditions, we can have this green function in this form, and if we want to make a solution for this that equation under these conditions, so y of t, that is the amplitude of a function, because now we know what is g is our green function from these initial conditions. You now know that what is our green function in this case looks like, that is g is equal to 0, and this is so what we are using here, that our function is 0 and the first order derivative of a function is also equal to 0, that is dg by dt is also equal to 0. And here we are using after the derivative, after we take the derivative, that the time is equal to 0. So this is under these initial conditions, the green function, our green function, that is t and t prime, is equal to these two inputs. And you see that the interval we have chosen between t prime and t, where in this interval from 0 to when t is greater than 0 and less than t prime, we have the green function equal to 0. But when the interval changes and we have t prime is greater than 0 but less than t, then we have this sine impulse. So this is just the showing us that it is just the impulsive force over here. So as I said, the solution of the second order linear differential equation is then with these initial conditions, that is y naught is equal to y naught prime is equal to 0, is this thing. So here you see that we have replaced g in here with 1 over omega sine omega t, because we had g, if you remember here, here in this equation you see we have g over here. So we have just substituted g for g the value we obtained, and also change the integration limits. So you see that in here now that we have changed the value of g, and also the integration limits also are also changed. So this is the complete solution we have got. So we knew the value of green function, and this value of green function helped us to put the integral or the final solution in this form. So now we consider another example of a green function to solve a certain kind of a function, certain kind of a second order linear differential equation. But now this equation is a little bit different. You see that before that we had omega square over here and that forcing function, but now we don't have omega square, we have just y and the forcing function in here. So what we want to do is to solve this equation with the help of a green function. So the first step is to think about the initial conditions. And what are the initial conditions in our case? That we have the amplitude or the solution of this function, that is y is 0 at x is equal to 0, that is the independent variable, and at x is equal to pi by 2. So y is 0 at both x is equal to 0 and x is equal to pi by 2. So these are our initial conditions which we will be using. And in these initial conditions, the physical interpretation of such a system is that you can think of a string that is stretched along the x-axis from x is equal to 0 to x is equal to pi by 2. So let's say along the x-axis I have some kind of string. So here I say that this is at x is equal to 0, and here I am using pi by 2, x is equal to pi by 2. So this is a string which is stretched there. So what we would like to see, that if this string vibrates, so how can so this is the physical interpretation for this equation. Then we have some forcing function, and we have a stretched string in these limits. So what we would like to solve this equation, and think of it that we release this string and it vibrates with a force, and when it vibrates with a force, then it has a certain kind of vibrations with different amplitudes and different components. So we sum up of all those components, and let's say this is the forcing function we have. So it's a periodic function. So this forcing function is a periodic function of sine type, and the y gave us the amplitude of the vibration. And what now we want to do is to solve with the help of a green function this equation, and get the value of the y. And in a green function, if I replace y with a g, in this equation. So what we will get that with respect to x square second derivative g, and so here before it was y, I replaced with the g and green function and the g here, and this is the Dirac delta function. So this satisfy these boundary value conditions or boundary values, that is g at x is equal to 0 and g at pi by 2 is equal to 0. So same conditions, remember the same conditions as we have applied for the y for the amplitude of the vibrations, the same conditions we have applied for the green function, which is this one. So what we get is this solution y. Now you see that under these limits, that is from 0 to pi by 2, 0 to pi by 2, we get g x prime to f. So this is the solution we have, and for any g or any x when x is not equal to x prime, when they are not equal, I mean we are talking about the point where x is not equal to this x prime, what we get is a green function. It becomes of the form that is a sine omega in this limit. So you see when x is greater than 0 and less than x prime and less than pi by 2, then it is a sine function. Green function becomes a sine function, and in this limit the green function becomes a cos function. So we see this is somehow the construction of the green function in these limits. So I have sketched for you this over here, the green function, the amplitude of the green function with respect to x. You see that the amplitude or the green function increases as we go along x-axis, and but this over x prime we see the sudden change, and then rather than increasing it start decreasing, and on pi by 2 it becomes 0. So over this point the behavior of the green function abruptly changes, and at x is equal to x prime over here, since it is continuous, it's still continuous. So at this point at x is equal to x0, that although it is continuous, but it changes its behavior at its and it comes down. So you can think of a vibration of a string, stretched string, as we were considering, that when string is vibrating, then its amplitude can go from plus to minus or change its behavior, and then we can use the green function to model it. At that point when x is equal to x prime, so both of the solutions, that is cos and sine, are equal at this point, that is a x prime is equal to sine x prime is equal to bx prime cos x prime. So these are some references you can look at, and at the end I would like to summarize the whole procedure we have learned today is about Green's function. So remember that whenever you have a second order linear differential equation and you want to solve this equation, so there are many methods available for the solution of such equations, but one of the very robust and efficient method is of the Green functions. And Green functions provide you not only physically interesting solution, but also they are mathematically very efficient. So what we do is we take a forcing function and construct our Green function in the second order linear differential equation, and transform it into the integral with the help of Laplace integral. And then what we can do is that simply replacing our y with g help, and g acting like on f like an operator gives us our solution. So in this way we can we only need to construct our Green function, and then difficult equations which are otherwise very difficult to solve with other methods are readily solvable with the help of Green function. So with this I thank you all.